quiz opens today, right? That's happening. All right, so one quick announcement on the scheduling of drugs from the last lecture. So, yeah, I should help with the slide. Just know for those, the 5 categories of scheduling, and then whether they have projected medical benefits and potential for abuse. Those are the only things. Don't worry about all the examples and knowing each of the drugs, et cetera, et cetera. It's more about just understanding that there are 5 classes or 5 different schedulings, and then whether or not they have accepted medical use or potential for abuse. That's the only thing for that one. So, and that's it. Any questions or concerns before we dive into opiate land? Good for now. Cool. All right. Opiates, here we go, big ones. Yeah, so we did CNS depressants, got into the mild hallucinogens with the cannabis. Now we're in for the heavies, analgesics as well as euphorians. Opiates, I tried this one as a outline, a timeline. But what, good 7,000 years ago, earliest mention of opium poppy cultivation, primarily in what's now the Middle East, and then grew out from there. But this plant, the opium poppy, has been known for millennia. It's the sap from the flowers in this plant. Can be used for medicinal purposes as well as psychostimulant purposes. So the, I guess, earliest recording in 300 BC that Greek medicine refers to this as a narcotic. That's actually where we get the term opium from. Opos in Greek means juice, so that juice that spills out when you cut the bulb of a flower is, yeah, where all the magic comes from. Laudanum was a very early opiate to use, so now jumping up, yeah, a whole bunch of time, but in the 1660s. So this was used as an analgesic, as well as around that time this was big for dysentery. Since one of the major side effects of opiates is constipation, early doctors or medicine folks were using it to treat diarrhea because it causes constipation. So that was some of the earliest use. But then, the beginning of the 1800s, the German chemist isolated morphine from the juice of the opium poppy and found that that was the main active ingredient in the plant itself. Also named from Greek, Morpheus, the god of dreams, is where morphine comes from. Also, I guess if you're a fan of the, what were those movies? Neo and whatnot. Anyways, doesn't matter. But then Merck capitalized on this several years later and was able to isolate a lot of morphine, as well as chemists started figuring out how to synthesize this. And coincidentally, the discovery of the hypodermic needle in the 1860s was a huge boom in this field and to total detriment of society. Because until this point, people had been smoking it, or drinking or smoking isolates and tinctures and condensation from, or condensed preparations from the sap of the plant. But now people were able to mainline this drug. And when this became an IV drug, the issues with addiction and the problems with toxicity from this really became apparent, because smoking it and drinking it provided a certain amount of dosing, or a certain type of administration that would definitely get you high and get you addicted to it. But with the introduction of intravenous administration of these drugs, everything really changed. So after that, there was a lot of interest in this drug, as we'll talk about a bit in this lecture, due to the types of semi-synthetic molecules that were able to be, you could take a precursor molecule or morphine and then change it into heroin, and this is what really caused a lot of problems. I'll get into that in the lecture. So we actually have things to look at. But the opioid receptors were cloned in the early 90s. These are some of the earliest receptors cloned in the big boom of molecular biology that happened in the 80s and 90s. But this had a lot of interest just due to its effect, the psychotropic effect with society, as well as it being used as an analgesic. And even today, a lot of current formulations of opiates are used as painkillers in clinical settings, and this is, it's a huge benefit to clinical application, and it's a big problem with addiction, as a lot of people have heard, especially over the last 20 years. But yeah, that's a brief history of this class. So, compounds themselves, like the cannabinoids, there are endogenous opioids and there are exogenous opioids. In terms of endogenous opioids, ones that we make, enkephalins, dynorphins, and endorphins. All of these, the minor ones aren't as important, but what is important, and we'll reemphasize this through the lecture, there are 3 different classes of opioid receptors, delta, kappa, and mu. Delta are primarily hit by enkephalin, dynorphins primarily hit kappa opioids receptors, and endorphins primarily hit mu opioid receptors. Don't worry about nociceptin receptor, we won't go into that. It is, just as a quick aside, this is an amazing receptor class that is currently being pursued for pain relief due to the fact that a lot of the nociceptin agonists have incredible ability to kill pain and no narcotic effect. There's no inebriation that comes from it, very little to any toxicity and dependence so this is an amazing field right now, but still very academic. You don't really hear a lot about it, definitely out in the mainstream press. But back to the lecture, I'll reemphasize this because each of these endogenous opioids do have potency at other receptors, but just remember, enkephalin is primarily for delta, dynorphin is primarily for kappa, and endorphin is primarily targeting mu opioid receptors, okay? Then over on the right, this shows naturally occurring semi-synthetic and synthetic compounds. Morphine, codeine, the most popular, so these are isolated right out from opium juice, if you will. Semi-synthetics have to usually use one of these molecules as the base. Well, really, morphine is the base. And then that structure, or on that scaffold, you can build other opioid molecules. Fully synthetic ones, methadone, fentanyl, these are, as we'll see, they're just generated in a lab, and they're not built off of some scaffold that you can actually isolate from an opium poppy. So, but that's just a quick rundown on those. To reiterate, so these are the actual sequences, so these are actual peptides. The endogenous opioids I just mentioned are actual peptides that are produced in our body. Don't worry about these sequences. These are just the 3-letter abbreviation for the amino acids in these sequences. That's not important. Just remember enkephalins, endorphins, dynorphin for delta, and endorphin targets mu, enkephalins the kappa targeting opioid. And then a bit of background on these. Enkephalins and dynorphins, widely distributed throughout the brain and a lot in the PAG or periaqueductal gray. So looking deep in the midbrain here is where the periaqueductal gray area is, and then there's projections down the spinal cord, sensory nerves out into the periphery, et cetera, et cetera. As this says here, enkephalins activate mu and delta. Dynorphins are for kappa, but just remember, as I said, mu is primarily for endorphins, enkephalins deltas, and dynorphins kappa. That'll come up in a table. I'll bring that. One that's really important, I'll bring that up in a bit. But then for the endorphins as well, largely restricted to pituitary or activation from there, then it can go into circulation. Endorphins do hit all three of the opioid receptor subtypes, or they have potency at each of the three, but mu is the primary one that it hits. And a lot of this is just kind of background on the endogenous opioids. Outside of which of those three classes hits the three different types of receptors, the background isn't as important as the exogenous opioids that we'll get into, as the exogenous opioids are the psychotropic ones. So, in terms of where the receptors are expressed, mu and delta are actually expressed on the cell body of a neuron, while all three are expressed down at the terminal. And then a big thing to know, similar to our CB receptors, activation of all three influences calcium channel functioning, and this essentially works as a neuroinhibitor molecule by influencing how the calcium channel will function. Talked about that before, and so just like the cannabinoid receptors, here's a opioid receptor. This is a GPCR, and a couple to the G-alpha proteins here. But as you can see, binding of an agonist dissociates the G protein trimer. Here it's listed as alpha O. I mentioned before the IO family, there's a lot of blurring between that. Just know that it's coupled to G-alpha I. We'll get to that in the next slide. But what's important here is it's actually the beta gamma subunits here that are the ones that are activating the ion channel. So again, we're blocking calcium channel, activating potassium channel, and then all of the fun that elicits happens downstream from that. So, again, coupled to, so opioid receptors are GPCRs, coupled to their G-alpha trimer, G protein trimer. G-alpha I will shut down adenylate cyclase. Beta gamma can influence ion channel function. All right, so that's true with the cannabinoid receptors as well. When we're talking about adenylate cyclase modulation, that's a G-alpha protein situation. Ion channel modulation is primary beta gamma protein subunits, okay? But here again, morphine is coupled to G-alpha I, so it's going to shut down adenylate cyclase, blocking cyclic AMP production, prohibiting PKA from being turned on, and then the subsequent loss of gene expression. Here's this figure that I keep bringing up over and over again, so you can imagine all of this downstream stuff stops due to the fact that this is coupled to G-alpha I. Here we're seeing G-alpha S, so all of this stops due to the fact that opioid receptors are bound to G-alpha I. Okay. Where are these in the brain? They're all over the place in the brain for the most part. All three forms. So we've got mu, we've got delta, and we've got kappa in their respective. What mu's orangish, delta is green, kappa's reddish. You can see in these different areas, for the most part, all three are expressed all over the place with the exception of some areas of the PFC and down well into the stem, which has just mu and delta, but yeah, you're not going to be quizzed or expected to know each area of the brain that has these. Just know that they're fairly ubiquitously expressed throughout the brain. Okay. Now what this actually does is no surprise. Effects of opiates. Euphoria is the big thing that people get addicted to, right? We'll get into activation of reward pathway, which will be no surprise. But that's the main thing that people go after. Whereas analgesia or pain relief is what it's known for clinically, or that's what it's used for clinically. Also has been used for restlessness and whatnot in order to get people to sleep, because one of the early clinical applications of this was as a treatment for alcohol addiction. So people, as we studied before, people get addicted to alcohol, they're on alcohol a whole bunch, and then all of that inhibition happens, and then upregulation of calcium channels and glutamate receptors and vesicles trafficking glutamate. Person goes off alcohol, they have the delirium tremors because the glutamatergic tone goes way up in the brain and blah, 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 and people can't sleep and they're all restless in that. You give them some morphine and they go right to sleep. But problem is, or it comes to this class, opioid withdrawal leads to craving of opiates, irritability, restlessness, increased GI motility is huge. If anybody has had the misfortune of seeing someone who has used opioids for a long time, especially very heavily, and then stops, or more specifically is given an opioid antagonist that just blocks all receptors, it's ugly. People get incredibly sensitive to pain, very loud and angry, and then those who have been constipated for a while just start to void, and it's all kinds of messy and smelly. But those are, some of the effects of withdrawal. So getting into the PK analysis, absorption variable routes of administration, primarily oral or inhaled, but then also IV administration, so various routes. Distribution, it goes wide, it can get all over the place, including through the blood-brain barrier. Talk about that in a bit. Several different enzymes hit this. So CYP3A4, the most popular one, then 2D6 also gets this, and then UGT, this is just a glucuronide transferase, and don't need to worry about that, just know it UGT. So these three enzymes will metabolize this. Large first pass effect, so the majority of this, 60 to 80% is metabolized during its first pass in the liver, or through the first pass metabolism. And then second pass in the glucuronidation, there is a glucuronidation of this enzyme can allow for stability of the opiate molecule, and we'll get into that in a little bit here, with two different sites on the molecule being targeted by a glucuronide addition, primarily M3G, as this says here. And as you can see here, the morphine has a very short life. A more stable glucuronide, or M3G version of this molecule, lasts a lot longer. And again, we'll talk about that in a bit. But these are all eliminated through the kidneys, so we just pee them out after they're broken down. Okay, so in terms of PD analysis, so all of the stuff I showed before about receptors and this and that, those are all well and good, but again, I really just want you to know enkephalins for delta, endorphin for mu, dynorphin for kappa. Switch that around. Anyways, you don't need to know this whole graph, okay? What I would like you to know is that mu comes in mu1 and mu2 forms. mu1 is primarily for analgesia, mu2 is primarily for everything else that it does, okay? Pain relief comes from mu receptor isoform 1, that toggles analgesia in a person. All of the other effects of opioids come from mu2, and then the rest I'm not so worried about. Okay, but this just describes the different types of agonists and antagonists here. Again, you don't need to know all this table, just know that these are agonists and naltrexone, naloxone are antagonists, and we'll get into that. So don't need to know structures again, but morphine here, the base molecule, and the one that's really has the most physiological activity, the rest need to be converted into that, and we'll talk about that in just a bit. But here's heroin here, and you can see it's the same molecule, but it's just acetylated at these two positions. And heroin is actually known as diacetylmorphine in the chemistry circles, but We'll talk about why that's important in just a minute. And then you can see here for the antagonist, so these are both agonists, antagonists, same molecule for the most part, just a little extra spinach off here, and then it completely freezes the receptor. It's amazing such little molecules can have such a profound effect, but they do. So on heroin, this is a really interesting drug. So as I said, this is diacetylmorphine. You have these two acetyl groups here. Once one is cleaved during a first pass, or this can actually happen in the brain too. You get 6 monoacetyl morphine, so 6 MAM. And then the other acetyl group is removed to produce morphine. And this is the one that's really active in the brain. From here you can get, again, 3-MG and M6G, M3G or M6G from that. All have certain amounts of psychoactivity, but morphine is the main molecule. And then when looking at plasma concentration plotted as a function of time, you can see heroin and the 6 MAM have very little circulation time. And it's really because they're converted to morphine very rapidly, and morphine is allowed to do all of the effects. And heroin was initially created, I think I said that, when morphine began to be a problem, or when clinicians saw that people were getting addicted to morphine and the problems that opioid addiction causes, medicinal chemists tried to manipulate this molecule and see if they could come up with an opioid that would provide the pain relief they were looking for, but wouldn't have all of the side effects as morphine. They came up with heroin, and it was just a total Pandora's box because it's more potent, it gets across the blood-brain barrier quicker. They substituted that in and found people immediately took to it really well, but then started having a lot more problems with it than they did with morphine. So really kind of, shot themselves in the foot, if you will. And yeah, as I was mentioning, so morphine can get across the blood-brain barrier fairly easily. Heroin does in a big way. Then the M6G can as well. But the issue here is that heroin actually doesn't have potency at the opioid receptors. It has to be converted to either M6G or morphine in the brain before it's actually active. So again, here's diacetylmorphine or heroin. That can get in, then it gets converted to morphine before it actually is active. And as just a, so opioids were a huge thing, right? Before the 1900s, there was a lot of interest in it, and then terrible abuse in society, and it kind of tapered off after a while, especially after the Second World War. There's always been kind of a prevalence in society for addicts, for opioids, but it kind of tapered off. And then by the 70s and 80s, cocaine really took off. That was huge in the 70s, 80s, and then into the 90s, that started to taper off, and then opioids came back with all of the designer molecules and pain medicines that were being created, because that was really the start of the current opioid crisis that we're going through now. The only reason I bring that up is due to the fact that for a long time, it got really popular, definitely 100 years ago, but then became very adulterated, and a lot of the, illegal trade had very impure opioid preparations. And as this says, heroin in the 70s contained only about 4 to 8%, so less than 10% actual drug. And it was still active because it was being administered intravenously, so there was a little bit in there, but it was enough to get people high. But then by 2000s, heroin on the street was greater than 80% pure. So that started causing a lot of problems because people were overdosing a lot easier because there was a lot more drug in there. But the other thing was people switched from IV administration to pill form. and then went back to IV, which has been really interesting. But the point is that part of the problem we've been having is due to the increase in purity that's happened. And people that had been long-time users got used to taking X amount of drug, and then as the purity started to increase, they were still taking X amount of drug, but then overdosing more because there was a lot more opiate in their mixture, and they weren't used to that. So, I don't know, that's an anecdote for you. But, yeah, so just remember, heroin is the most potent compared to morphine, but heroin isn't technically active at opioid receptors. It has to be converted to morphine for it to have a pharmacological effect. So here's some more pictures of stuff. Obviously, you don't need to know structures. Just know that these are more of the oral drugs: codeine, naloxone, Vicodin, OxyContin. And then you can see how close they are in structure to the big ones, morphine and heroin. Then the true analgesics that really were formulated for oral dosing. The others can be dosed, people make kind of a condensed version of the sap to smoke it. People put it into a liquid form to shoot it into their veins. But then a lot of clinicians wanted to use it more as just a pill that they could prescribe, because orally prescribed medications are just a lot easier to work with than other things. So these are all formulated as oral forms of opiates. And you can see the potency table here comparing oral versus parenteral administration. Parenteral administration is anything other than oral, in this case, mostly IV. And then inhaled. But as you can see, some of them, they didn't even bother to test because they don't have an actual, they won't be administered through any other way than through pill form. But you see the difference between taking a pill and then shooting it up, if you will. You need less of it for these parenteral applications. But again, the same thing applies here with these opioids. They need to be converted to morphine in order to have a effect or be an agonist. And as you can see, codeine really just has to have a removal of that methyl group before it's morphine. But yeah, we don't need to know structures. They're just there for people who are interested in that. All right, fentanyl. I need to ask everybody who's still listening to me for a personal favor, all right? At the count of 3, I'd like you to say fentanyl, all right? 1, 2, 3.
Fentanyl.
Thank you. Okay, the word is fentanyl. It's not fentanyl. It's not fentanyl. If you're folksy or whatever the accepted term is, don't listen to the people in media and the politicians. This isn't an alcohol. It's not fentanyl. It's fentanyl, okay? Please spread that far and wide. Very high potency opioid, as you can hear all the time in the news, because this is really adulterating a lot of opioid supplies as well as stimulant supplies. It's been surprising to hear how many Adderall prescription are being laced with fentanyl, and just across the board. It's really scary. And then, is that in here? Remifentanil is another one that's coming down the pipe that's even more potent than fentanyl. But here again, just a comparison of the potency or dosage of the different types of opioids. You'll see some distinct differences between the values on the previous slide and here. They're just for reference, not going to be tested on that. It's just something to look at. Yes, please.
Okay, so you said it's in stimulants. Is there any chance it's in any caffeinated beverages at the store?
Oh, I hope not.
It better not be, because I'm a regular consumer of those.
Well, yes. I don't believe they've been found in any just food products. I'm sure, you can find stories on it, but it's about more of the prescription drugs. You know, there's a lot of adulteration for street preparation of opioids with fentanyl, and it's understandable why. You know, if you're selling heroin to someone and you know, you lose your supply or you want to make more money or whatever, you can cut it with fentanyl and then you, just put baby powder or, bicarbonate or something in there to fill the rest of the mass. And then, from what I understand, this chemistry is very easy to accomplish in just a couple of steps. So precursors for this are easy to acquire. Synthesizing fentanyl in a lab is very easy from what I understand. So, you know, as a someone who is selling this on the street, I can understand why you would use this rather than the actual morphine or heroin. But that's where you see most of the adulteration. It's in opioid preparations, and then medicines that don't come from a trusted manufacturer. What the point I was making is that it's not just opioids anymore. There are stimulant drugs. There are the amphetamines and those like drugs that are being cut with this. And that's really confusing because they're such different, they'll both trigger the reward pathway, but they have such different opposite acts. They act so oppositely on our brain and our bodies that I don't know why someone would do that, but whatever. Enough soapbox. So, fentanyl, high potency opioid. You can see the variation because this is a fully synthetic molecule, so it doesn't look like this at all, but hits the same receptor with much higher potency. Methadone, another synthetic opioid used to actually treat opioid disorder, and this can reduce craving in time, and the magical part of methadone is in its dosing and its ability to stick around in solution. So as you see here, when looking at subjective high plotted as a function of time, heroin has these peaks and valleys, right? You shoot up, you go way up, and then you go way down, and you crash, and you start to go through withdrawal, and you go way up and up. Methadone usually keeps you in a more normal range of feeling, but this is if you are dosing properly, and for the most part under clinical, most people that are on methadone treatment have to go into the clinic, then they get their daily dose, and then they're good for the day, and they come back next day, et cetera, et cetera. But this is how it works. You don't have the big highs and the bad lows. You kind of stay in a normal region. So it'll scratch that itch, if you will, but it won't really get you high. But then when you come down, you're not down in the dumps and craving it. But that's kind of the magic of this specific opioid. And yes, it is important to note, cross-tolerance with morphine and heroin can come from long-term methadone use, just like the rest of the opioid drugs, all right? Yes, please.
Isn't methadone self-addictive too?
So that's interesting. Is methadone self-addicted as well? So it can be. It absolutely can be. And this is definitely by individual cases. People who are more sensitive to the effects of these would be more prone to addiction to these. Those, especially who've been desensitized for a long time or just don't have as sensitive a system as others, don't tend to get addicted to it. And it's really because of this. You don't tend to get the highs from it, okay? So, that two parts of addiction, you're chasing a high as well as you're running away from the punishment of withdrawal. You don't get the withdrawal, but you also don't get the big highs. But yes, so simple answer, yes, you can get addicted to this. There are definitely cases of people reporting addiction to methadone, but it's very rare and it's system specific. So that's a long way around for that one. Good. Okay, as far as treatments go, naloxone and naltrexone have been developed. These are antagonists, so they're going to block opioid receptors from activation, primarily administered as a recovery agent. So Narcan, you get that all over campus now. At least I've seen it handed out, I guess. But used as an inhalant for treating opioid overdoses, and then naltrexone can be the same. Naltrexone is higher potency than naloxone, but being antagonists, they don't have any efficacy, right? But as mentioned before, this is used as a treatment for alcohol addiction, but yeah, its success rate is kind of dodgy. Suboxone is a really good one. This is one, you know, every once in a while the science community really gets their act together and actually have a good idea. And they deserve credit for that. But this is developed due to opioid abuse problems that people, so one of the big problems that people are having now with orally administered opioids, so pill form, is that people start taking the pills, they get addicted to the pills, and the pills aren't enough. So they take more pills and it's still not enough. So they start to smash up the pills and they start to shoot them up. They start to do IV injection of the pills because it gives a quicker high and but that's bad. You know, then you have a much more or higher propensity for overdose or the toxicities of opioids if you go through IV administration. So medicinal chemists came up with Suboxone, which is a combination of buprenorphine and naloxone. So naloxone is the antagonist we just talked about. Buprenorphine is a partial agonist at the mu receptor. So being a partial agonist, it just gets partial efficacy, right? So it's enough to take care of the cravings, but not enough to really get a person high. So the beauty with this, though, is that they're both administered in the same pill. If someone takes the pill and they eat it like they're supposed to, they get the effects of buprenorphine because naloxone is very sensitive to stomach acid and it gets broken down in the stomach, and then the rest of it gets passed out in the small intestine. The buprenorphine gets absorbed in the small intestine and then it can go into circulation and actually get into the brain and take care of opioid cravings. However, if you take the pill and you smash it up and you shoot it into your vein, then naloxone will block everything. So, and you don't get the effect of the buprenorphine then because naloxone is sitting in place on the receptor, not allowing anything to happen. And this is really, I thought this was a very smart formulation of it. So you have two opioids being delivered, an antagonist and a partial agonist. If you take it as you're supposed to, as an oral medication, you get the effect of buprenorphine. But if you use it as people are not supposed to, but it's a very common way that you crush it up and shoot it into your veins, you only get the effects of the naloxone, the antagonist, and you don't get any effect. So, that is pretty clever. So, morphine activates VTA dopamine neurons. We've talked about that, right? It acts on the VTA that goes on the nucleus accumbens and the PFC. That's its primary activity for the reinforcing effects. And then we'll finish with this one. I'll do this again, hopefully not, it's an okay department of redundancy department. Here's our dopamine neuron that's central to this whole thing. Dopamine is under the control of the GABA neuron in the VTA under normal circumstances, but it synapses on this dopamine neuron in the nucleus accumbens and this dopamine neuron, or this glutamate neuron in the PFC. Once this releases dopamine and activates these, glutamate then feeds forward to dopamine, turning this into a circuit. Under normal circumstances, the GABA neuron is shutting off dopamine, but we have opiates on board binding to the mu-opioid receptor. It'll shut down the GABA neuron and allow dopamine and this whole circuit to turn on. And the last thing, here's your pharmacological term for the day, disinhibition. Disinhibition is when you're inhibiting an inhibitor. So remember that. The opioid is providing disinhibition into this system because it is inhibiting the GABA neuron that's inhibiting dopamine. So, disinhibition, word for the day. That's it for us. Have a good weekend. Good luck on the quiz. Let me know if you have any questions or anything.